Good evening, everyone. Welcome to MAPS, our final MAPS of the fall 2021 semester. And I just wanted to thank everyone who is here live and everyone who is tuning in to watch later on. I just wanted to, before we start with our speaker, just give a shout out to the people at MAPS who were recently, last Saturday, we were in the Modesto Celebration of Lights. So here is our float that we made for MAPS to celebrate our science talks that we've been bringing to the local area for 30 years. And also the 100 years of MJC. All right, and I also would like to make some announcements about the upcoming spring lineup. It is on our MAPS website. Keep tuned in to the MAPS website for details. We are doing our first 2 talks of the semester live. So we want to have both a live component at the MJC East Campus Auditorium and also some YouTube streaming available as well for both of those talks. The first one coming up is January 28th. It's Dr. Danielle Lee Cantrell, who works preserving and studying ecosystems in the Palmyra Atoll. So that should be really interesting. And then February 25th, our second talk that's going to be live in the auditorium, the meteorologist Dirk Verdun, and a panel discussion on weather, climate, and the impacts on the environment. So keep an eye on our webpage for details on those 2 talks. All right, and so I'd like to introduce Dan Chase, astronomy professor at MJC, who will introduce our speaker.
Hello, I'd like to introduce our speaker for tonight. Dr. Margaret Turnbull received her PhD in astronomy from the University of Arizona. She developed the HabCat along with Jill Tarter, a catalog of potentially habitable stellar systems. Her work continues to be an integral component in the search for life in the universe. She's the 3rd MAPS speaker that has an asteroid named after named in their honor. So asteroid 7863 Turnbull, so the 3rd MAP speaker there. And in 2018, Turnbull ran for the office of governor of Wisconsin as an independent. So I'd like everybody to welcome our speaker, Dr. Margaret Turnbull.
Thanks, Dan, and hi, everybody. Welcome. I was hoping that I could maybe just get to know the people who are online right now. I think we have like maybe 30 or so people who have joined. And I'm just kind of curious to know, is everybody in California, and how are you doing tonight? And maybe just tell me, like, you know, are you in high school or middle school? Are you in college? Are you done with all of your education? Give me a quick chat and just tell me, like, anything at all about yourself. And maybe you could throw in, so, you know, like, if you have a particular interest in astronomy or particular questions that you're hoping we could talk about tonight, you know, feel free to throw that in as well. And our coordinators here will let me know if you are responding to me at all. And I think while hopefully people are responding to me, I'm going to go ahead and share some pictures to be a part of my presentation tonight. Okay. So let's try that again. There we go. Great. So I can actually see that some people are responding here, and I see that some people are in college. Jennifer's watching with her kids and husband because we all love astronomy. Yay! And we've got a couple college students at Modesto and MJC, and a math professor is on the line, and an elementary teacher, math specialist, awesome. Junior in high school is with us, and student at James C. Enoch's High School, awesome. College student in California, somebody who believes that there is intelligent life on other planets and would like to talk about that tonight, maybe. English professor and elementary school teacher, excellent. So thanks, everybody. I look forward to seeing where our conversation goes tonight. So I'm going to talk about what I know how to talk about, which is this question of, will there ever be another Earth? So my specialty is in looking for planets around nearby stars, and especially looking for Earth-like planets around nearby stars. And, you know, as we go along in the talk tonight, please feel free to type questions in the chat. So it's a little hard for me to talk and watch the chat at the same time, but I will be stopping periodically just to see what questions are there. So please don't hesitate to ask the things that pop into your mind as we go along. So I am at the SETI Institute, which is actually based in Mountain View, California, but I'm talking to you tonight from northern Wisconsin, from the cabin in the Northwoods, which is where I'm spending most of my time right now. And in the last 3 days or so, we got about 15 inches of snow, so it's like prime cross-country skiing and snowshoeing and everything. So that's been like really on my mind. But I will say, I also, when I was walking last night right around at dusk, and I kind of got way out there and a little bit turned around, and I hadn't brought my phone, and there's so many trails back in the woods up here. I had to rely on my dog to get us back home. And when the temperature is dropping and it's getting down to like 10 degrees, 5 degrees, 0 degrees, and you've got your down coat on and you think you might be able to live through the night if you don't find it back, you start to think a lot about, like, do I live on a habitable planet? Because I know that I need a lot of support to be here. So that's the context that I'm working in up here. And it's simultaneously beautiful and also like a little bit terrifying. So, but the Earth is such, such an incredibly amazing planet. And the more that I learn about planets around other stars, and the more I learn about other stars and what the stars themselves are like, the more I come to really appreciate what we have here. And I will say that although my curiosity about other worlds and whether they could support life or not, it has only grown the more that I learn. Right in step with that, I only have come to appreciate our living world more and more because, I think, spoiler, I think I could tell you from the heart, there will never be another Earth. This is the one we have, and we grew up here, and we're really tuned for this planet. And there may be many living worlds throughout the galaxy and beyond. In fact, I hope that there are, and I don't see any reason why there couldn't be. But that doesn't make our own home any less unique or special or appropriate for us to be able to live on. So let's see if I can get my slides to advance. There we go. So let's just get let's just get ourselves oriented here. So this is our planet. This is Earth, obviously. And I don't know if this picture looks familiar to anyone, but this isn't just any old picture of the Earth. This is the first picture of the fully illuminated Earth that was taken by the astronaut crew of Apollo 17 on their way to the moon. And it happened to be that flight occurred at a time when the Earth and moon and sun were approximately aligned, so that when they turned around to look at the Earth, they saw the fully illuminated globe of the Earth. And this picture, just a billion people saw this picture, and it really inspired and galvanized the modern environmental movement, including concerns and regulations around clean water and clean air, because it was just such a stark reminder of this beautiful blue marble that we live on, suspended in the emptiness of space. And, where else are you going to go? This is it for now. This is what we've got. And it was a really inspirational picture for a lot of people. But you'll see this image. This is the most reproduced image in the history of digital photography. And if you pay attention, you can start to recognize the cloud formations and atmospheric circulation and the snow in Madagascar, and all of that is recognizable from that particular day, December 7th, 1972, when this picture was taken. So this is our world. It supports a lot of life. All the life that we know of depends on liquid water, the presence of liquid water. There are living things in Antarctica, and there's not a lot of liquid water there. But in the dry valleys of Antarctica, where it's really cold and really dry, it's still colder, or it's still warmer and wetter than Mars. So it's still more habitable than Mars. And the Atacama Desert of Chile, which gets almost no rain. I mean, it's like a gentle fog that comes in every 100 years or something. There are some microorganisms that live in the soil, but the Atacama Desert is wetter than Mars. So just to put into context, maybe we should just go live on Mars. How fun would it be to go to Mars? I don't think it would be a lot of fun, honestly. I think it would be super interesting, but I don't think it would be a lot of fun. And I think that, I would probably just want to come back to Earth as soon as humanly possible, because it's so nice here. But that kind of puts into context, what we're talking about. But life seems to be able to survive really extreme conditions. I mean, we find life at the bottom of the oceans, in hydrothermal vents. We find living things, microbes, at least in the Atacama Desert, and in certain little niche environments. In the dry valleys of Antarctica, there doesn't actually appear, that may be at about the limits for life as we know it. There doesn't appear to be much living there other than what has flown over, and bugs or things that have stopped there and are just dying. But life has taken hold anywhere that you have liquid water on this planet. Life has taken hold in some form, even in otherwise really extreme conditions, and found ways to adapt. So we think of liquid water as being sort of the great enabler for lots of different kinds of life forms to arise. And this is our star. Let's see if I can get a better view here for myself. So this is our sun. Less remarkable at first glance to look at. It's a white orb. To your eyes, this is what the sun approximately looks like. It's a yellow star, and at least in visible wavelengths, there's not a ton of features or anything super interesting to look at, except for the sun has sunspots on it occasionally that come up. These are colder spots, just due to the way the gases are circulating in the sun. But what we can do is look at the sun in different wavelengths to get a more nuanced picture of what a star is really like. And so what I'm going to play for you is a video of the sun. And this is a compilation of images taken by the SOHO satellite. So this is actually a European Space Agency satellite that went into orbit around the sun, took lots of pictures at all different wavelengths. And what I'm going to tell you first, what we're going to see, and then I'm going to show you, and then I'll probably show you again because it goes by a little bit fast and it's super interesting. And the first thing we're going to do is we're going to start out looking at the sun as it appears through our eyes. And the sun will be rotating, and we'll see a couple of sunspots go by. And then we're going to start shifting into shorter and shorter wavelengths. So we're going to go into the ultraviolet, and we're going to go into the X-ray. And it's really interesting because the sun in X-rays is actually black. It's very dark, except for where magnetic activity is causing extremely hot gas to loop along magnetic field lines. And you'll see that and how weird that looks. And then what we'll do is we're actually going to block out the sun with a little metal disc inside the camera of SOHO. And then you'll be able to see the solar wind streaming out. We call that the corona of the sun. And at the very end, we put it all together and you'll see what a star really looks like. This is what a star looks like. So our sun is a star and all stars are suns. And if you really look carefully at what's going on in the video I'm about to show you, you'll see other stars in the background, and maybe you can kind of start to imagine what those stars look like up close as well, and that they are all just like this. So let me go ahead and play. So I'm going to go ahead and play it again because I really feel like this is where you don't get to see this view of our star very often. And I think it's just worth letting this soak in a little bit. So, you know, again, this is starting out with wavelengths that our eyes can see, and the sunspots will go by. But then just try to notice even more, try to pay attention even more, and try to just notice, like, what kinds of things do you see at different wavelengths that you can't see with your eyes normally? And what other things are going on in this video that raise questions for you? Even just little things like, why does the imaging suddenly become so ratty at the end of some of these clips? You know, what do you think is going on there? And if you have questions or ideas, go ahead and type them into the chat. Chronograph on so we can see. Personally, I feel like I could just watch that video all night and be happy. I think that stars are beautiful and amazing things, and we kind of just, we take it, we take it for granted that we have one and that it's just there every day. It's just the same. But the reality is that the sun is changing over time. It has changed pretty significantly since the Earth originally formed, the Earth and the rest of the planets originally formed. And that's an important piece of the puzzle when we ask questions like, how is it possible that the Earth has remained habitable for the last 4.5 billion years, really, the entire, almost as if it was made with simple life forms already on it. I don't think that is necessarily the case, but it seems to be that even in the earliest rocks, there are signs of living organisms on the Earth. So when we think about how a planet's climate can remain stable over that long of a time period for all these different kinds of life forms to arise and then go away and new life forms replace them, and it just evolves and evolves and evolves, you have to also think about how the sun is changing over time, which it definitely is. I mean, it's got its own life cycle. All of the stars do, and there's really no two the same. So continuing on, that's our planet and our star, and this is our planetary system. And maybe, if you Google the solar system and try to find a nice image or a nice graphic showing, nothing is any good. I mean, this is the best I could really come up with because it's a nice representation of what each of the planets look like. And actually, the sizes are pretty much to scale here. So you see how little the Earth is. The Earth and Venus are about the same size, and they're bigger than Mercury and Mars. Mars is a very small planet. And you can see how little they are, compared to Jupiter and Saturn, and how small Uranus and Neptune even are compared to Jupiter and Saturn. I was just talking with a colleague yesterday, actually, about how interesting it is and unusual, seemingly, that we have two giant planets that are about the same size on nice circular orbits in our solar system. But maybe could you type in the chat right now, people who are seeing this, why would I be unhappy with this image here? I mean, it's about the best I could find. Planets are to scale size-wise with each other, but what do you see that is definitely either missing or incorrect with how the solar system is represented here? And I would love to hear your thoughts about that. And maybe while people contribute to the chat, because we do have like a 20 or 30 second delay, I'll fill in a little bit with some just interesting perspective maybe about other planetary systems and what they look like and compared to ours. And when I was in college at the University of Wisconsin-Madison, I was in college from 1993 to 1998. And the very first planets around other stars were discovered in 1995. And the people who were looking for those planets, they were using a way of seeing those planets that would measure the gravitational perturbation on the star that the planet was creating. So just by having a planet there, the planet and the star go around the common center of mass. So the star does move a little bit when the planet is orbiting around it. And if you have very, very, very precise measurements, you can actually see that. Everybody thought that this team of scientists from California was crazy because they were looking for such tiny movements. And even if they got their measurements calibrated accurately, the only kinds of planets they would be able to see would be really giant planets orbiting very close to the star, which everybody can plainly see is not how planetary systems are set up. I mean, look, we've got Jupiter and Saturn as our two giant planets way far out in the system. It takes some 10, 20 years to go around one time. You take you forever to make a measurement like that with this way of making measurements. And so, it was kind of, that team of scientists was kind of, I wouldn't say ostracized, but like maybe openly mocked, within the astronomical community. But they, nevertheless, they persisted, and they actually discovered, they discovered, the first planets, and they were big, and they were orbiting very close to their star, which completely turned upside down our whole understanding of what planetary systems could look like, and that they could be very different from our own. So, some people are saying, looking at this picture, like the planets don't usually all line up in a nice row like this. That's very true. I mean, they can align, but that would be for like one little instant, and then they're immediately on to the rest of their motions. All the dwarf planets are missing. So, when I was in high school, Pluto was a planet. It's now considered a dwarf planet. It's a member of the trans-Neptunian orbiters. Pluto actually does cross Neptune's orbit along with a number of other small bodies. And we know that extending outward beyond Pluto's orbit, there are more objects like Pluto that are all on pretty elliptical orbits like that. So Pluto is still important, but it's a member of a belt of Pluto-like objects or dwarf planets. Let's see, all the moons of all the planets are missing here. The asteroid belt is missing. So between Mars and Jupiter, there are asteroids. Really though, if you took all the material in the asteroid belt and put it back together into one planet, it would not be, if I'm remembering this correctly, it's not even as much material as what would make up our own moon. So it's not a lot of stuff. And sometimes when in movies, people fly through the asteroid belt, it's like, oh, we have to dodge and whatever. The reality is you probably would not even know that you were going through the asteroid belt because all of them are so far apart. Somebody says, the distance is not right. So this is totally off base. I mean, in fact, the one thing that I would say is really missing from this picture is space. There's no space between all the planets. They're all crammed together. That is not realistic at all. If you were to rise above the plane of the solar system and look down, say, at Jupiter and Saturn going around the sun, Saturn is like twice as far away from the sun as Jupiter is. You would not even be able to see the terrestrial planets because they would all be lost in the glare of the sun. All the terrestrial planets orbit so close to the sun, and then Jupiter and Saturn are much further out and further out. There's just a lot of space. If you ask me the question of what is our solar system made of, I would say it's primarily made of empty space with a few small planets in it as well. Let's see. Arnold is reminding everybody that the Great Valley Museum has planets to scale, at least by size, in the lobby. In Madison, you can actually go on a solar system run. We have a lot of athletes and runners that do this. They'll say, meet me at Mars, and we're going to run to Neptune today. And it's great because they're all lined up on the sort of multi-use bike/running path. And it goes out of town for like 10 miles, 10 or 15 miles. And, Neptune and Pluto are way the heck out there. So if you're training for a marathon, running the solar system in Madison it really gives you that sense of how far away the planets really are from each other, especially the outer planets. Okay, so moving beyond our solar system to the whole big family of stars that our sun is a part of. Here's the galaxy, and this is the galaxy in the nighttime sky, as seen from the south rim of the Grand Canyon. And, I just want to emphasize that all the points of light in the sky there that this picture is capturing are stars, and they are all stars like the sun that most, if not all of them, have planetary systems of their own. And the reason why we see this band of light in the sky, I'm sure many people know, but I'll say it anyway, is because we are embedded inside of our galaxy, which is like a flattened disk with a brilliant bright bulge of stars in the middle. If you could rise up above the plane of the galaxy, which we currently can't do, but we can imagine it and make artist renditions of it. And we have lots and lots and lots of real data that helps us do this accurately. But this is what it would look like if you could rise up above the plane of our galaxy. And all of the light coming from the galaxy is coming from stars, and every one of those stars has some sort of companion, most likely, either as a multiple star system or as a planetary system. And actually, most of the light in the galaxy is coming from stars that are brighter than the sun, and which is interesting because most of the stars in the galaxy, the vast majority of the stars in the galaxy, are small stars. They're small red stars that are smaller than our sun, and they're called red dwarfs. But 75% of the stars in the galaxy are just these little small red stars. I mean, they're bigger than Jupiter, but not that much bigger than Jupiter. And the vast majority of stars in the galaxy are red dwarfs, but they emit almost none of the light. I mean, they're very cold and they don't burn hydrogen very quickly, and they don't emit a lot of light. And by cold, I mean, a couple thousand degrees. So at their surfaces, whereas our sun is close to 6,000 degrees at the surface. And that makes a big difference when you're thinking about life and where a planet would have to be around that star in order to be warm enough to host life. But that's the vast majority of the stars. The vast majority of the light coming from the galaxy is from much hotter stars than the sun, and there's not that many of them. There's maybe 3 to 5% of the stars in the galaxy are these hot blue stars that are emitting actually most of the light in the galaxy. And we have a nearby galaxy too that is not so different from our own, the Andromeda galaxy, that you can see with your eyes if you're in the right place. It's just kind of a fuzzy blob, but to a telescope, it would look like this in the sky. Or to an EV scope. If you've heard of EV scopes, they're kind of all the rage now. They let you take these really amazing pictures from your driveway in the middle of the city. And I recently bought like 4 of them to give away as prizes to people in the astronomical community who were developing new algorithms to figure out how to find planets around nearby stars. So, and they've got this huge citizen science program going now, and they regularly issue challenges to people who have bought EV scopes. And I think they're very straightforward to learn how to use and give you amazing views of the nighttime sky. And they work by actually capturing light over time and integrating so that you can start to see deep sky objects like, the Andromeda galaxy. But this is how big it would be on the sky compared to the size of the moon. The full moon. And I like this picture for a few reasons. One is it just gives you a sense of scale. If you could see Andromeda really well, that's what it would look like. And of course, Andromeda, very similar to our own galaxy, has about 400 billion stars or so, 300 to 500 billion stars. And again, most of those stars are small red dwarfs, but probably about 10% of them are stars like our sun, and then most of the light is coming from even brighter stars, and just a few percent of the population. But every single one of them has something around it. And then here's our moon for scale, and I like this because if you've ever gone outside at night and seen the thin little crescent, either right before new moon or right after new moon, say like 3 to 5 days. If you're up early in the morning, I guess that would be before new moon, early in the morning, before sunrise, or right at sunset, just after new moon for a few days, you can see this thin little crescent, and you'll notice that the rest of the moon is actually illuminated too a little bit, and you can see the dark part of the moon. And that's what's shining on that is the Earth. The Earth is shining on that. We call it the Earth shine. And this is actually even a topic of research as well. You know, when I was in grad school, I had a question, you know, what does the Earth look like from very far away if you have no spatial information? It's just a pale blue dot. And you look at that light and you examine the colors. Can you tell that there are continents and planets and plants and clouds on this world from very, very far away? And that light shining on the dark part of the moon is very similar to the kind of light that we would be receiving from a planet around another star. It's all jumbled up. There's no spatial information, but you can look at the colors. And in fact, you can see the plant signal. You can see the vegetation signal. You can see that there is water on this planet. That is all, those are all signals that are in the light of the Earth that is shining on the moon. Here's a close-up of Andromeda, just to give you a sense of what we're talking about. This is a real picture. I had this hanging on my wall for years, all through college and grad school, because I just thought it was so profound to be able to look at another galaxy and just see, you know, 400 billion stars, and imagine, you know, this ocean of light coming from all of these stars, and what kinds of life forms could possibly get going in that system? What could there be? But again, you know, galaxies, just like our solar system, galaxies are mostly empty space. The stars are so far apart from each other. If you collided two galaxies, which actually happens all the time because galaxies are not very far apart. They're pretty big compared to how far apart they are, and they do collide all the time. Happens constantly. But when they collide, no two stars will run into each other because there's just so much space in between the stars within a galaxy. So, you know, just sort of remind ourselves that, you know, the universe is mostly space. So what I've now done is I've placed a tiny little red box in the sky next to the moon, just for scale here. So this would be about like the size of lunar Maria that we are very familiar with, one of the dark patches on the moon. And if we zoom in on that and ask, well, what's in that? You know, what would we see if we zoom in on that? Which Hubble did do, actually, as part of its purpose for existing was just to do this, was to find a little tiny little patch of sky with nothing in it, no stars, no known stars, just empty nothing. Look between all the stars in the galaxy out into the furthest reaches, and what do you see? Well, you see thousands of more galaxies. Even so, you can imagine every single little patch of sky, the size of this little red box, you know, just tile the whole sky in little red boxes. Every single one of them has this many more galaxies in them. So there's a lot of real estate in the universe, you know, as far as stars go, and possible places for planets and life to arise. At this point, maybe what I'll do is just stop and see if there are any questions in the chat. Right now, I'm having a look myself. So yeah, I see that somebody does have, and Dan is saying that somebody does have an EV scope. That's great. And that MGC will be using it for their telescope viewing during the science nights next semester. So that is great to know. And the Andromeda galaxy is possibly a little bit larger than the Milky Way, but they're pretty similar to each other. Let's see, so Earth shine on the moon. Oh, I see, yeah. So somebody comments that the Earth shine that we see from the moon is getting incrementally dimmer in recent times because the reflectivity of the Earth is changing as the climate changes. I also have heard that. It kind of saddens me to think about that. And I'm not sure how, I'm not sure of the magnitude of that change, but I think that is a published result and is, with, outside of the error bars. So I think that that is real and that is happening. I'm not sure how well understood it is at this point. And let's see, will it ever be possible for humans to travel to other galaxies? Well, maybe this would be a good time for me to just tell you about my little theory about that. I don't know if people have heard of the Fermi paradox, but the Fermi paradox is, Enrico Fermi was a physicist. He had lots of great ideas, very famous in all physics-related fields. But the paradox is, if there are intelligent civilizations, if intelligent civilizations do arise on a regular basis, if life is common, and then at least once in a while an intelligent civilization that can travel between the stars does arise, then by now, because the galaxy, is 13 point something billion years old, and we're pretty young as a civilization. I mean, we're basically like 100 years old. We just got radios like a century ago, and only recently it became possible to even really, talk to each other across the planet, let alone between the stars, let alone traveling to the stars. So you could imagine we should be one of the newest, youngest civilizations in the galaxy, which means that most of the civilizations out there have had a lot longer to figure out how to travel between the stars. Some of them have had, even relatively young ones would still have had like millions of years to figure out how to do that. And if in 100 years or so, we're already sending things to Mars, why haven't any civilizations just colonize the whole entire galaxy? Why aren't they here? And the paradox is said as, where are they? If they exist, then why aren't they here? And, I just want to emphasize how far the stars are apart from each other. They're really far apart. Going to Mars is nothing like going to another star. I mean, that is so much easier, and it's going to take us a while to figure out how to get a human to Mars safely and actually living there, self-sustaining. And of course, Mars is not the ideal environment for that, but even if we did find another habitable planet around the very nearest star, to go there would just be such a farther trip and so much more work. And my theory about this is that because it's so hard to travel between the stars, you basically have to be a peaceful civilization in order to pull that off. You have to work out all of your stuff that causes you to self-destruct and to disagree and to self-defeat and to fall apart. It's kind of like a house divided type of thing. It's so difficult, and it requires so much coordination and so much efficiency of resources and whatever, that you've got to. My theory is that this just doesn't go very well for inherently aggressive civilizations, and that aggressions you have to evolve out of that over time. You have to mature to the point where you can actually do that heavy lift of traveling between the stars, because it's so far. And maybe by the time you figure that out, you no longer have the desire to just pillage and plunder. Like, maybe you're just enjoying and traveling, and if it's not going to be helpful where you go, you leave them alone, and or maybe even help them in ways that will not upset them. But so my thought is, like, they could actually be, common in the galaxy, and we wouldn't necessarily know that because of the character that civilizations have to evolve into before they are ready to travel between the stars. But to get around to your original question about the galaxies, that is so much even more of a lift to try to get between the galaxies. I think that we would just have to discover some whole new way of moving between the stars. You know, I just watched Dune last night, where they figured out mentally how to fold space, you know, through these altered states of consciousness. And it's like, you know, it sounds like you know, it sounds ridiculous now, but who's to say, you know, that there isn't something along those lines that we won't come across that enables this in the future. Otherwise, it'd be very hard to take this body, which really belongs on Earth, and transport it throughout the whole, you know, let alone just to another star, let alone to a whole nother galaxy. That's a very long way of saying I have no idea. So I think that that's kind of it for the moment. And I'll try not to like keep you here all night. I know I was supposed to be done talking pretty soon. And I wanted to just like look at something together, which is the concept of a habitable zone. So the sun emits light, which all life on Earth depends on in some way, shape, or form. So even the microbes and creatures that live at the bottom of the ocean, where there is no sunlight at all, and they're living around hydrothermal vents and getting their energy from the heat of those vents and from the chemical energy of those hydrothermal vents, even they actually indirectly do depend on the sun, because they have metabolisms that require some level of oxygen that is dissolved in the ocean water. And the oxygen that is dissolved in our oceans comes from photosynthesis, photosynthetic plants and algae. So everything on Earth is at least indirectly dependent on the sun. And all of the living organisms that are known on Earth, even the weird ones that live at the bottom of the ocean, all depend on the presence of liquid water. There are even microbes that live in ice, but they are living on in little pockets of tiny amounts of liquid water that are able to persist because there are salts in the ice. So nothing we know of is not dependent on liquid water and the sun. And the place around the sun where the temperature is right for liquid water is what we call the habitable zone. So the Earth is in the habitable zone. And in this picture, this is showing the orbits of Mercury, Venus, Earth, and Mars. And then the green band here, the brighter green band, is showing the sort of conservative estimate of where the habitable zone is. And then the darker green band is showing a more optimistic estimate of where it could be. So if you put the Earth within anywhere of this whole annulus around the sun, it would still be a habitable planet. If it went too far beyond Mars, it would certainly freeze over. And if it went too far inward of where it is right now, we would probably lose the oceans to space, because we would suffer a runaway greenhouse effect where the Earth is just getting so much energy from the sun that more and more water is evaporating from the oceans. And then water vapor itself is a greenhouse gas. So then even more heat is trapped, and the oceans evaporate even faster. So you suffer a runaway greenhouse. And we actually are already near the inner edge, very close to the inner edge. In fact, like 10 years ago or 10 or 15 years ago, when people were using climate models to not just model the Earth as it currently is, but then play around a little bit with, what would happen if the sun suddenly became brighter or we moved closer to it? It was interesting because it appeared that perhaps we were not even in the habitable. We were already like right, at the inner edge, if not a little bit interior to it. And the models have been improved since then. So the Earth is now safe and it's a habitable planet. I'll breathe a sigh of relief. But that's the habitable zone around the sun. And you can imagine that the hotter stars have habitable zones that are further out. They're emitting more light, they're hotter, and planets are going to be warmer at any given distance. So an Earth-like planet would have to be further out from that star in order to be a habitable planet. And then for the vast majority of the stars in the galaxy, we talked about this, the red dwarfs, which make up, 75% of the stars in the galaxy, they're so much cooler and so much fainter that a habitable planet would have to be very close to that star. I mean, it was so close that its orbit would be well inside that of Mercury. There is a famous nearby planetary system that has like 7 planets in it, and 3 of which might be in the habitable zone. And everybody's in love with this one star and all of its planets. It's one of these little faint red dwarfs, and all of those planets have orbits that are well within Mercury's orbit. So like all 7 of them. I think the furthest one out is at like 1/3 of the distance from the star that Mercury would be. And that's where the habitable zone is, though. So there's a couple planets that seem like they're in the habitable zone of that star, and they have orbits that it only takes, a few days to go all the way around the star. And that's, that is interesting because there could be all of these planetary systems out there where these they're just packed with planets, little planets, terrestrial planets. Multiple ones could be in the habitable zone. You could imagine life forms figuring out how to travel between them because they're not even that far apart, actually, much closer together than the planets in our solar system. And just colonizing, 3, 4 planets and having all of these living worlds in one system. It's super interesting. But again, it's very small. And I'm going to skip over this stuff about Kepler because even though it's like really interesting, it's also kind of time consuming. It's basically just telling you that a lot of the planets we found are around these very small stars. And interestingly, a lot of the planets we've found are actually in size. They're between the size of the Earth and Neptune. We call them super Earths. And we don't have anything like that in our solar system. So we don't really know exactly how to model it or what its climate would be like. Would it have a solid surface or would it be more gaseous? And we're starting to get a better handle on that now. But it's just really interesting that the one kind of planet we do not have in this solar system seems to be very common elsewhere. But I'll just wrap up with another word about these planets that we're finding around red dwarf stars. The news every week, it seems like there's another article about how we found we found a planet that could be Earth 2.0 or something. And so far, all of them have been around these very faint little red dwarf stars. So right away, I'm telling you they're not Earth 2.0 because they're not around Sun 2.0. They're around a different kind of star. And when your orbit only takes you like a week or something to go around that star, what happens at those small distances between the star and planet is that the planet will become tidally locked. This is very similar to our moon being tidally locked to the Earth so that we always see the same side of the moon facing toward the Earth. And that would happen to the planet so that there would always be a side that was like in the sunlight, daytime, and there would always be a side that is forever in darkness. And all the climate models say that you would end up with a desert on the near side and an ice cap on the far side. And in fact, most of them suggest that all of your water would evaporate off of the near side and it would all freeze out on the far side, so that it would not be a habitable planet, even though technically it's at the right distance. But more and more as we look at it and the nuances of climates and how heat transport can work, it seems like there could be a zone of habitability around the edges of planets like this, even if they're tidally locked. But you can just imagine how different that would be, and how organisms would be different, and what would the wind patterns be like on a planet like that, and would there be migration? Because you wouldn't have seasons, right? Nothing's really changing, or would it change? And what kinds of things could happen on a planet like this, and what would that mean for the kinds of life that would then arise? And the other thing too, that's, if you remember back to the movie that I showed you of the sun and this corona streaming out, this high energy radiation coming from the star. These red dwarf stars are known, even though they're so small, to be even more active than the sun. So if you're going to be that close to a star, I'm thinking, you need to be pretty tough as an organism and be able to tolerate a lot of radiation and, very high rate of, heavy particle fluxes, and just, be very good at repairing your DNA or whatever your information transport molecule is. And there's, so those two things, in my mind, make red dwarf planetary systems highly questionable, but they're kind of all the rage right now because that's what we know how to find. And you hear about it a lot in the news. So I'll just pause there and maybe just stop there actually and see if any other questions have come up. Well, somebody's asking when the Milky Way and Andromeda inevitably collide, what will be the result? A single new galaxy comprised of the stars of each of the original galaxies? Yes, probably. I think there's some pretty cool movies online. If you Google simulations of, you can even specifically Google simulations of Milky Way and Andromeda collision, and those models do actually exist, and they'll kind of pass through each other. They pass through each other, and then they get all distorted, and there's arcs and streams of stars, and there's a lot of new star formation is actually triggered by that. The dust and gas gets compressed, a lot of new star formation happens. You get a whole new generation of young stars and planetary systems. And then eventually they kind of, they go around and around and they eventually do settle into probably an elliptical galaxy. And let's see, so if Europa or Titan, say, have life forms, would they be derived from objects transporting material from water's habitable zone, or the gas giants originated in that zone previously? Yeah, so good question. Europa is, I think, the most interesting place in the whole solar system. It's a frozen over moon of Jupiter's, but we know that it is a water world. It's got an icy shell on top of a circulating liquid water, saltwater ocean that has more water in it than all of our oceans combined on Earth. And it's being heated from within by tidal forces as it orbits around Jupiter. And the four big moons, the Jovian moons, perturb each other just enough that it keeps them all on slightly elliptical orbits. And so they all have this sort of tidal massaging going on from Jupiter's changing gravitational force as they're closer and farther and closer and farther in their elliptical orbits. So they definitely have an energy source. They have liquid water. I have heard it said that if there is life, it might not be complex life, though, in Europa's oceans, because it is probably an anoxic environment. There's not enough light at that distance from the sun for there to be photosynthetic organisms, especially not under a 100-kilometer thick ice shell. But I say never. I would love to see us melt a probe through the ice and fly or swim a camera around and see if there's any fish, personally. I think it'd be great. And Saturn's moon Enceladus, very similar situation, actively outgassing ocean water to space through the cracks in its ice. And that has actually been flown through by Cassini. And it appears that there are organics in that water that's outgassing from in the interior of Enceladus. And then Titan, I think, is so fascinating too. It would have to be a completely different kind of life system altogether, being so much colder water exists only in the form of rocks on Titan, but there is cryovolcanism, and there's a whole atmospheric circulation, I guess you wouldn't call it hydrological because it's not water, but it's methane. It's a methane ethane system with lakes and seas and rainfall and snowfall and rivers and stuff. So I think that is really interesting to look at. And I believe that NASA has chosen, at least in concept form, to look at another probe to Titan that would either fly around in the atmosphere or float around on the seas. Let's see. If the red dwarf systems are easy to see, what systems are hard to see? Thanks for asking that question, because normally when I'm not laying so much ground foundational information, that I would dive directly into that question. That the reason why most of the planets we know of, the terrestrial sized planets that we know of, are orbiting red dwarfs is because the way that we're finding them is by looking for transits. So the Kepler mission and now NASA's TESS mission, they have been observing continuously thousands of stars, looking for the shadow of a planet passing in front of it. And if that happens, it's a very small change in the brightness of the star that you can see, just because the planet is passing in front of it, it looks a little bit dimmer. And that change is very small. So you have to have a very stable observatory, and you can only do it from space. But it works the best for these little M dwarfs, because an Earth in front of an M star or red dwarf, they are also called M stars, is a bigger change than an Earth in front of a really big sun-like star or an even hotter, bigger star. So it's easier to see the transits in front of a red dwarf happening. And the other thing is that because the planets are so close, the transits are happening every 5 days, and you can instantly get confirmation. Whereas the habitable zone around the sun, it takes a year for the Earth to go around, and you've got to wait 3 years and get 3 transits to prove, that scientifically that you have definitely discovered a planet in the habitable zone of that star. And that's why Kepler did not result in a lot of Earths around sun-like stars, because the Kepler mission failed and died just as it was getting to the point where it would be able to do that. So going into its 4th year, when it would have been just getting able to make definitive confirmations of Earth-sized planets around sun-like stars, that's when the mission died. So we don't have that from Kepler, and TESS only flew for, that was a very short prime mission. So that's not going to happen with TESS either. What we need to do is fly a telescope that can just take pictures of planetary systems. And that's really challenging to do. That's a new technology that we are working on. And I have a team that has been helping build a camera to do that with the next space telescope, the Nancy Grace Roman Space Telescope. So we're going to test out the technology in space and see if we can make it work to at least see Jupiter-sized planets around sun-like stars. And then from there, we want to fly, some kind of flagship mission that would be capable of taking pictures of Earths around sun-like stars. So that's the seemingly long, but actually very short explanation that hopefully made a little bit of sense. And let's see. What methods is SETI using to search for extraterrestrial life? So the SETI Institute does a lot of different kinds of astrobiology related research, and maybe mean especially intelligent life. And the Allen Telescope Array is still operating. But I think that the Breakthrough Listen team is probably doing the most, and that is SETI is in collaboration with them, but it is not leading that. So I'm not sure how much like dedicated telescope time they actually have for listening. But my mentor, longtime mentor, Jill Tarter, and I have talked about this. I mean, a portion of my dissertation, PhD dissertation, was in designing a new target list for the SETI search using the Allen telescope array and listening for radio signals specifically. And the Allen telescope array has, I'm actually not even sure like what the status is right now, the functionality of it. I mean, it's been somewhat online, but it still hasn't been completed to the original, the original specs that everybody was hoping for. So Jill has said that basically where we're at right now is if you were to go dip a glass into the ocean and look at the water and determine from that there are no fish in the ocean, that is about where we're at right now as far as how much listening and searching we've actually done for intelligent life in the galaxy. We've just only barely, not even really scratched the surface on that. And I think what is needed there is a very long-term, multi-generational search effort just to even begin to sample the whole search space that's out there. Are there any planets of interest in the search for intelligence? I think that of the known planets, so all the known planets, so there's thousands of known exoplanets now, and hundreds of them are probably terrestrial planets. They have sizes that would be consistent with a terrestrial rocky planet. And then of those, there's dozens that look like they could be in the habitable zone. And as I said before, almost all of them are around red dwarfs. So there's some real concerns for habitability, tidal locking, and then flaring, stellar flaring. But in order to even get a sense of whether any of these worlds, what they're really like, what their climates are really like, we just need we need direct imaging. It's called direct imaging, where we would just take pictures directly, and then we could analyze that light, very similar to the way that we look at the Earth shine reflecting off of the moon, and can actually see signs of water, oxygen, photosynthetic activity, other things that would help us to understand what their climates are really like. And even over time, if we are able to take a picture directly of a planet, even if it's just a speck of light, over time, we can see how that light changes, and it gets fainter, it gets dimmer, it changes color. All of that added up together would allow us to make a really crude map of the surface and start to get a handle on whether or not there are continents and oceans and other stuff. In the James Webb Space Telescope, so Tim is asking, does JWST have instrumentation to study the atmospheres of transiting planets? It does, and will do that for sure. Again, it won't be Earth-like planets around suns. Those transits are too shallow. The Earths are just very small compared to sun-like stars, and so there's not enough signal there in order to extract information about the atmosphere of an Earth-like planet orbiting a sun-like star. But plans, absolutely, I'm very confident that will be like one of the first things that many of my colleagues want to do for these dozens or so of, at least maybe not dozens, but there probably, I bet there are a dozen favorably transiting planets where the transit is actually deep enough, but the star itself is still bright enough and nearby to get a good signal out of that. And people will jump on that right away with JWST, but it's not going to be like hundreds of stars. And it's going to be like 10 papers, and each paper is going to have 500 authors on it. And then that will be done. That's what I predict. Well, I think we're getting, so organizers, maybe you could chime in about how we're doing time-wise, and if this is a good time to fold up.
Well, I was just going to thank everyone for the questions too. And then I know that when you were showing the whole set of slides that you had before, you had like some teams at the end. Maybe it would be a good lesson for people to know that there are definitely lots of teams of people working on these, if you wanted to show those. Or
sure, I can share some photos. So here is I have a little diagram here, the little cartoon diagram of some of the basic optical components in the camera that we're building and will fly on the next space telescope after James Webb. And this is a telescope that is like a copy, almost in some ways, of the Hubble Space Telescope. But it will have a camera on it that is designed to take pictures of planets around sun-like stars, and we're at least going to try to do that for some giant planets and test the technology, but it's incredibly complicated. So that's actually the camera in the background being built and installed into a vacuum tank where we can start some of the initial rounds of testing. And in fact, that's from a few years ago. So this is all of those hurdles, those technological hurdles have now been passed, and the mission was just last month, actually. It's successfully transitioned into phase D, and phase D is the final phase before flight, where we're cutting the metal. We're cutting metal, the real metal that's actually going to fly into space. So no more prototyping. We've done all of our tests, and it's ready to go. So that's me with some of the engineers in the background. And this is my team of scientists, and we're all looking at which stars we should look at with this camera once it's successfully built and flown, and which planetary systems would be the most promising to get good pictures of. And there are a lot of young people involved in the team as well. These are the people that I bought EV scopes for as prizes, because they joined us in this data challenge where I gave them really, really good high fidelity fake data that had planets buried in these messy images that we expect to get back from the camera. And these people all developed algorithms to be able to extract the planets from those images. And the ones who did the best job, they were the ones who won the EV scopes. And then this is even bigger, the bigger team of people who are involved in the mission, including project managers, people at the Jet Propulsion Lab. This is actually taken, I think, in Greenbelt, Maryland, where we had one of our meetings near NASA Goddard. And so NASA Goddard and JPL are the two really big players. And then NASA has funded a bunch of science teams like mine. There's two teams that are building this coronagraph to take pictures of planets, and then everybody else here is all working on galaxies and star formation and other kinds of astronomy topics. And we're let's see, we wanted to just show you as well some more lab pictures. So this is actually at the Starshade lab at the Jet Propulsion Lab, and the idea is that we might even be able to do this with the Nancy Grace Roman Space Telescope, but if not, this would be an idea for a bigger flagship later, where we actually fly in space in its own orbit around the sun, pretty far away from the Earth, a telescope, and then we fly a second spacecraft, actually much larger than the telescope, basically a giant piece of Kevlar, but very carefully shaped into this sunflower-like shape that creates an extremely deep shadow. And when we align it with a star, it makes a deep shadow around the telescope, so that the telescope does not receive any of that starlight, but it does still receive the light from the planets that are right next to the star. So that would also enable you to be able to start to see planets, Earth-like planets, around lots of different kinds of stars. And then because that is such a giant structure, we have to figure out how to make it fold down really small. So we're using origami to find folding patterns that will allow us to maintain this very precise shape when it's unfolded, but when it's folded up, it can be very small and fit inside of a realistic launch fairing, because you can't launch, something that's like 100 meters across into space. You have to fold it up little, like maybe 10 meters across, and then figure out how to deploy that with while retaining the shape. And the shape is super precise. I mean, the Starshade Lab is actually kind of dangerous at the Jet Propulsion Lab. I mean, you can see this tip extending down here, and it has to be that way in order to cast the shadow as deep as you need it to be to see something as tiny and faint as an Earth-like planet around a sun-like star. So that's 3 of us from one of the Starshade teams. And then here it is, beginning to be constructed, a prototype in the Starshade Lab, and they were experimenting with all these different mechanisms and getting it all folded up, and then the petals wrap around, and there's exploding bolts that deploy it once it's in space. And here's I'll just show this last animation. One of the designs we were looking at was that it would fly with a small telescope, and they would actually launch together. And then they would separate, and the star shade would unfurl, and the telescope would turn around, and then the star shade would have to have its own propulsion, but it would be separated from the telescope by an enormous distance, like 100,000 kilometers. So that's why they can't be in orbit around the Earth. They have to be in orbit around the sun. But then when the star shade is aligned with the star, when the telescope looks at it, we can see planets orbiting around it. So that's the concept we're looking at for the long term.
Oh, well, that's really amazing. Are you going to test it out so you would test it out in our solar system, flying it towards the sun, or?
Yeah, that would have to be in an orbit that, let's see if I can get another sort of image of this. In order for the two to get far enough apart from each other, they would have to be at L2. This is a second Lagrange point, which is a point beyond the Earth that actually follows the Earth around the sun. So the Earth and the observatory with the star shade could stay in step with each other, but they would both be in orbit around the sun. So it would be a little further out in the solar system from the Earth.
Oh. Well, we're getting some comments that definitely looks like a really cool idea and a really cool design. So,
well, we just had our decadal review results come back. This is where every 10 years, NASA has a giant review where we look at everything that we've been doing. We look at the taxpayers and what they're interested in. We look at the reality of the budget situation, and basically rank all of the proposed projects that astronomers want to do. And the decadal survey puts forth its recommendations for large, medium, and small scale missions. And we just got the results back from this decadal survey, and this was recommended as one of the top highest priority objectives for the next 10 years would be for NASA to get going on a mission that could find Earth-like planets around nearby stars. And I think it's just because it's really interesting to people, and that's what they want to see this agency doing.
All right, well, I don't know if Dan has any other questions that came up. right. If not, I wanted to thank Dr. Turnbull. I know that all the people who have been here watching you live have been really fascinated and stimulated into asking lots of questions about this. And I know that a lot of the people that couldn't make it and are joining us later are enjoying it as well. So I wanted to thank you on behalf of MAPS and on behalf of MJC for coming out, I guess virtually coming out to join us tonight and share your work and a lot of the background on this topic. It's definitely a new thing for us.
Well,
And
yeah, thanks for having me. It's really fun to interact.
yeah, thanks so much for trying to keep up with us and trying to keep up with the chat. That's really impressive too. So and yeah, another reason why it's good to join all these talks live. So for people who are watching live, definitely join us again in January and in February. And yeah, we have a lot of people appreciating it and thanking you in the chat. And we hope to see you guys again for our spring lineup in 2022.
Awesome. Thanks, everybody.